please give a warm welcome to Dr. Hu.
Thank you, Carolyn. I have to say that I am so delighted to be here because this is one of my favorite museums in the whole world. And I'm glad you're here too. So what I'm showing you here, these are different colors. And there's nothing nano looking about them, but in fact their color comes from their nanoscale properties. These are solutions of quantum dots. I'm going to talk about different kinds of quantum dots, but it's a new way of making color by shaping materials and sizes at the nanoscale. And to your left, I have a couple of structures that my group makes. And they look weird, and they are truly at the nanoscale. So that's truth in advertising. And as you see, most of it looks gray. This is what it's supposed to look like when it lights up. But to talk a little bit more about what we do in my group, we make boxes for emitters at the nanoscale. And these are 3 of the boxes that we make. We make something called a microdisc. We make a nano ladder with holes in it. And here is a dimension of 100 nanometers. We make something called a photonic crystal, and you can also see the size scale here, 500 nanometers. We make these very tiny structures in an environment like this. It's called a clean room. You have to dress up like that because the little nano boxes that you make are so small that if a piece of skin flakes off or a piece of dust or whatever flakes off on the device, it could kill the entire device. And then we measure our structures in labs like this, lots and lots of instrumentation. So a lot of big lab equipment to try and see something like color at the nanoscale. And this is Casey Russell and Zhongli Liu, who are 2 of the people in my group making those measurements. But I just wanted to set the scale for everyone. Something that we all know about, the diameter of a human hair. Does anybody know the size of a human hair? Do I have a guess? Say it louder. 600 nanometers. Oh, close. Millimeter? Yeah. 500, did you say? Okay. All good guesses. The diameter of a typical human hair, although it varies because we all vary, is about 70 micrometers, 70 microns. That's less than a millimeter, but it's about 70,000 nanometers. So it's almost 100,000 times wider in its thickness than a nanometer. Now, we're not going to today work at the nanometer, but there is an importance in understanding the nanometer for light. But first, before we go to what is nanometer about light, let's think about where does color come from? You could ask, does it come from nature? Like, we get flowers, beautiful flowers, and we grind them up, and maybe we can get color out of them. Or lots of things in nature have a natural color like this butterfly. Or maybe it's from the light. Actually, without the light, would there be any color? Or could we see any color? So light's pretty important too. Or maybe it's from our eyes. Maybe, and our eyes have to do something, have to, be in this loop somehow. And of course the answer is, it's from the interaction of all of them. And it has to be exactly the right interaction. So how do I know this? Could you distribute the goggles? So color has to have the input of all of it. It has to be the material you're looking at, and if it has a nanostructure or not, and it has to be the light and what kind of light you're using to look at it. And of course it has to go into your eye, and your eye has its own way of filtering light. So how do we know that's true? We're passing around some goggles, put them on, take a look and tell me, what do you see? Is there anything weird? Someone said, ooh. You've done this before. So I had the answer, it's splitting the light. Okay, what you should see is, you look around and suddenly you see rainbows everywhere. These are not ordinary goggles. They look transparent, they look like maybe the kinds of glasses you're used to wearing, but in fact they have a pattern of tiny lines etched into the lens. And those patterns of tiny lines are called gratings. And those gratings have distances line to line. They're etched into the plastic that's your lens. And those gratings are spaced on the order of a few hundred to a few thousand nanometers apart. So the message from this is something special happens when you have something at the nanometer scale in the material you're looking at, but there's reason why something special happens at that particular dimension, because if we ask what is nanoscale about the light, light is part of the family of the electromagnetic spectrum. Electromagnetic waves transported through the air or through anything. You know radio and television, so that's part of the electromagnetic spectrum that you use all the time. You may know X-rays when you go to the doctor. You know UV rays and you know to avoid them. But a very small sliver of that broad electromagnetic spectrum is visible light, which we respond to. There are other parts of the electromagnetic spectrum we respond to, but visible light has wavelengths from between 400 to 700 nanometers. So, how do we utilize this fact? We already know that something magic happens when you match light to something that has a natural nanostructure. So what do we do in my group? We make our own colors by making what are called quantum dots and quantum wells. Here's an example of a quantum dot. These quantum dots are about 30 nanometers wide and 5 nanometers high, about 100,000 times less than human hair, so it's very small. And I want to tell you how making quantum dots in a material can dramatically change it. So this is a piece of material. You can see right through it. Are there any guesses about what this material is? Plastic, glass. This is a material called gallium nitride. You can see right through it, so the question is, where's the color? But I'll tell you, and I'm going to show you later, that this material is at the heart of this flashlight that gives you blue light. And it doesn't only give you blue light, I'm going to show you later, it gives you, as you change it subtly, it gives you any color that you want. And so, how do we do that? We take that material that seems transparent, that seems to have no color at all, and what we do is shape little light emitters in the material that have dimensions on the order of 10, a few nanometers. And then we place these little light emitters into what I call a perfectly matched nanostructure. We put them in their own environment. And what does that environment do? And so here are examples of the environment that you've seen before. We call this a microdisc, we call this a photonic crystal. And that right environment, what makes it perfect? The perfection means that we have made that little environment, that little box for the light emitters to be resonant, to be exactly the right size for the wavelength of the light emitters in the box. So these quantum dots give out light at a certain wavelength, and then we put those quantum dots into a structure where the structure has exactly the same wavelength. A structure that is made uniquely for those little light emitters and therefore adapts to the tones of the nanostructure. And what's the result? Why is it good to match? Well, we get, just like when you have a flute and you have a really well-made musical instrument and you just play it exactly right, your breath is exactly right, and the acoustic wave that you generate is exactly right for that instrument, you get a beautiful tone. You do the same thing optically. You get something called resonance. When you match the wavelength of the color of the nanoparticle that you make to the wavelength response of the little box that you make. So you make actually beautiful music, only you make beautiful music optically. And you get true colors, just like you get true pitch, true frequency, that beautiful sound when everything is matched just right. You get control of the color emission. So what that means is, by making the right box and by controlling that box, you can actually make photons, make the light go out when you want to, not when it wants to. And that control is pretty amazing. And then, because of that match, these devices are more energy efficient. And what I mean by that, we're going from playing with color at the nanoscale to using color at the nanoscale and using some of these techniques. We get super efficient light emission because we can match. So for example, we've made lasers using those quantum dots in a photonic crystal structure with 100 nanowatts power threshold. Now, nano wavelength, nanoscale wavelength, nanoscale energy, watts is power, it's energy per unit time. Just to give you an idea, nano anything sounds amazing, but how amazing is it? So, I've been using a laser pointer, and there's a laser pointer here on the screen. So, does anybody have a guess about how much power, like in watts, I need for this laser pointer to generate light? And it generates light on me better than it does on the screen. Are there any guesses? Yeah. 300 watts. Microwatts. I have 300 watts, I have 5 microwatts. In the back, you're gonna have to yell out because there's a lot of noise. 50 watts. Okay. Anything else? Yeah. 30? Did you say 30? Okay. 30, 50, 305 microwatts. So, one thing to do is to look at what powers our laser pointers. And this is another laser pointer. Believe me, it's typical, and it's run by two 1.5 volt batteries. Okay, so that's 3 volts. And it has a current of about a milliamp, 1/1000th of an amp. So, if I use that, I can do a calculation, because power is current times voltage. And if you haven't learned that yet, you will learn that soon. So power is current times voltage. I have milliamps, 1/1000th of an amp times a volt. So that means this laser will take a few milliwatts of power. A few to maybe 10 milliwatts of power. So our nano laser has about 10,000 times less power. A milliwatt compared to 100 nanowatts. Now, I'm not being entirely truthful in the way that we can use them today, but the important thing is the possibility. Okay, let's go further. It's not only lasers, but we have devices called light-emitting diodes, LEDs. This is a light-emitting diode. It doesn't look nano, but the heart of its operation is nano. These are also flashlights made of light-emitting diodes. This is white. This is blue. Here, this is made up of light-emitting diodes, and if I turn this on, okay, I can get green, I can get red, blue, I can mix red, green, and blue, get orange, different colors of blue, purple, yellow. So this is a more powerful light-emitting diode that has multiple colors, and by adding those multiple colors, I can make any color. And basically, if I mix all colors, does somebody know what I can get? Yes, white, okay. So what I'm showing here is some work we did. There's still nanostructures. It's made out of this gallium nitride, which look completely transparent. And when we touch an electrical signal to one of these little microdiscs, we see it light up. And so this is an example of a possibility for a new kind of lighting, as you could see maybe from here. It's a new kind of lighting. And why is that important? Well, it's important because all the electricity we use today, all the electricity that's consumed all over the world, an amazing 20%, 1/5 of all the expenditure of electricity that we use is used for lighting, just so that you can stay up late and study, or you can read a book, or whatever else you need to use light for. And this is a composite image. It shows you, obviously it's not night all the time in the world at the same time, but this is a composite image. So it's taken over the entire 24 hours. The bright spots show you where people are using light. And so we need to get electricity from somewhere. And 20% of the electricity is used for lighting. A typical large electric power plant generates 100 megawatts of power. That means 100 million watts. So again, watts is power, that's energy per unit time, and then you integrate over time, and you get something like watt hours or kilowatt hours, and that's the total energy used. So here's a prediction. By 2027, LEDs for lighting could save 348 terawatt hours of energy. Does anybody know what tera means? Yeah. 1,000, more than 1,000. Much more than 1,000. Yes. You said 400,000? It's 1 trillion watt hours. So think about that. I mean, it's hard to imagine. If we go back, I'm coming to this in a minute, if you go back to a light bulb, if any of you have light bulbs, you think about 100 watt light bulb, 100 watts. And you keep this light bulb running all day. That's 100 times 24 to 2,400 watt hours. But think about 350 trillion watt hours. It's pretty much. And to put it in other terms, those are 44 electric power plants, and it's $30 billion by today's prices. So imagine the savings we would have in the use of our electricity. Imagine what we could use that power for in other terms, and imagine all the things like CO2 generation and climate warming that we could avoid if we were to go to a more natural kind of lighting scheme. Why do I say natural? So today, I'm sure, I don't know, how many of you still have light bulbs? A few of you, okay. So this light bulb, you can sort of see the structure. You can see the structure here. This light bulb gives light, but what it's best at doing is giving off heat. So what you do is you run electrons through the wires of that light bulb, and you make it really, really hard for them to get through. You give them a lot of resistance, and they get so tired they're generating heat, and finally they get red hot, and then we get light. But really, what we got light is at the end of a story that gave us heat. Then, how many of you have this at home? Okay, good. Compact fluorescent lighting. This is a way to generate light that's slightly more efficient, but there are issues with this too, like there's mercury in this lamp, and it's really hard to recycle this. And then we have LED light bulbs that look like that look like this, that you could buy at Home Depot, except the problem is they're a little bit more expensive. And part of the reason for doing the research we do is trying to make these kinds of light bulbs even more efficient but less expensive. So that's basically it. It's an introduction to a little bit of what my group does. And I have to say that we think that the nano future is so bright, we got to wear shades. And I want to say also that when I talk about playing with light, it's more fun to play with others. These are my groups at Santa Barbara and now at Harvard. And there are many more people over the years who supported some of the stuff that I showed you today. Also, it's good to have the funds to be able to do this kind of research. So we were very grateful to funding agencies like the Department of Energy, like the National Science Foundation, and again, other players and collaborators. I showed you my students, and these are the collaborators, professors at other universities and at UCSB that I've worked at. So thanks very much. Come up afterwards and take a look and ask more questions.